Alright guys, we are going to continue with the notes that we started the other day, and that begins with using a change of coordinates with polar coordinates to integrate over some cool regions that you would have had a hard time working with otherwise. So here's our first problem. We're going to take the double integral of x squared plus y squared dA over the region satisfying this little set of inequalities. First of all, this x squared plus y squared, this integrand, you can think of that as a paraboloid that's kind of coming out of the z-axis and opening upwards like a bowl. And then this region on the xy plane kind of looks like half a donut. It's an annulus. I have a better picture of it coming up soon, but essentially you want to think about kind of an annulus region and then with a paraboloid floating above it. So it's going to look kind of like an amphitheater of some sort of region kind of like that. Not a great picture, but I have a better picture coming up soon. So first of all, this would have been terrible to do in rectangular coordinates. But if we're using polar coordinates where x equals r cosine t and y equals r sine t, it turns out that what looks like a half donut to you here in RT space is actually a rectangle. It's a rectangle where t goes from 0 to pi, because you can see right here, excuse me, that our angle varies from 0 to pi, 0 to 180 degrees, and our radius r, our other variable r, goes from 2 to 5 consistently throughout our region. So it doesn't look like a rectangle, but in RT space that is a rectangle. So our double integral of x squared plus y squared dA in xy space becomes the double integral from 2 to 5 with respect to r and 0 to pi with respect to t. Now the trick here is you replace all instances of x with r cosine t, all instances of y with r sine t, and then you don't want to forget your area conversion factor. That's a small piece of mathematics that makes all of this possible for us. That's a little conversion factor that recognizes the fact that when you map between xy space and RT space, that mapping is non-area preserving, and that's a little adjustment factor that takes care of that. Now, what's cool here is cosine squared plus sine squared. You get a little Pythagorean identity there, so this blue expression reduces down to r squared, and r squared times r is just going to be r cubed. Now, if you want to take a look at what our little Roman amphitheater looks like, let me just erase all of this scribbling. And this is the region that we're finding the volume of. And it's described using this really simple double integral. That's what's beautiful about these change of variables. If you do a good choice of a change of variables, what might have been a very difficult problem becomes a fairly easy problem. And the volume of this Roman amphitheater is 609 over 4 times pi. I've mentioned this on Friday, but it's probably worth mentioning it again. But this whole change of variables thing, it's not just for polar coordinates. It's going to work for any sort of parameterization that you can come up with, any sort of mapping between xy space and uv space that you can think of. And the cool thing is you're like, well, how do I think of good mappings? Well, anytime you can parameterize a region, you can map that region to a new coordinate space. Now, this is the main generalized formula that you should be ready to use throughout this chapter. The good thing about this formula, though, is it's the exact same thing we did for polar coordinates. I just changed the letter r and the letter t to the letters u and v. This is u substitution, but it's uv substitution. So this should all be kind of reminiscent of what you did in Calc BC anytime you did u sub. And this might not look like the formula that your teacher gave you for u substitution, but it is. You replace all instances of x with an expression that depends on u. You replace your dx with a du, and then to account for the fact that the rate at which x changes is different relative to the rate at which u changes, we have this little x prime of u, a little expression that adjusts for the fact that a small change of x and a small change of u are different relative to each other. So you can think of the Jacobian determinant, the area conversion factor that we've been using. It's really just a higher dimensional analog of those little factors that we would have to throw into problems last year when we were doing u substitution. Here's a single variable example. You might like it, you might not, and that's okay, but this might help you see the analogy here. So here's an integral that I reasonably could have given you guys. Sorry about that. Pressed the wrong button on my stylus. Anyway, here's a problem I reasonably could have given you guys last year in Calc BC. You can use this u sub formula. Now this is going to look a little bit different than the u sub that you learned in your class last year, but I'm just changing the order of things to make it more similar to the method from this year. So if our f of x, if our integrand is natural log of x over x, I'm going to say that x of u is equal to e to the u. I know that last year you would have said that u is equal to the natural log of x. I'm reversing the variables there. I'm saying x of u is equal to e to the u. Well, natural log of x and e to the u, those are inverses of each other. So I'm just kind of changing the perspective here. Anyway, x prime of u is e to the u. So you could plug all that stuff in. So f, I'm going to keep that function the same, but I'm going to replace all instances of x with e to the u. And I need this x prime of u, which is e to the u. That becomes the integral from 2 to 6 of u over e to the u times e to the u du. Like I said, I know this looks different than last year's u substitution. It's the same work, but in terms of u's instead of more work in x's. And then you get your 16. If you don't believe me, try last year's u substitution method that you know. You'll get 16 as well, and you're going to see that while I was writing x equals e to the u, you were probably writing that the natural log of x is equal to u. Well, those are the exact same expression, just written as inverse functions of each other. And you can see right here, it is the same as last year. All right. So continuing on, when you guys are working on the lit sheet in this chapter, one thing they might ask about, linearizations. So you might see that word popping up. You might be wondering how linearization relates to a change in variables, but we saw it happening right here, right? We were approximating the area of a small region using the area of a small piece of a plane, a small piece of parallelogram. So just keep in mind, if you do see linearizations coming up in your lit sheet, we're really talking about this process where we found two vectors approximating the sides of the region we're trying to find the area of, and then we took the magnitude of the cross product of those two little vectors, and then we got an area of a parallelogram, which then approximated the gray area. And in the limits, those two areas are going to converge and be the same thing. So you might want to read B2 or B3 in the basics of this chapter if you see anything funky on the lit sheet that you don't know how to answer, but it really is related to this entire little proof that we did. All right, so let's move on beyond polar coordinates. What you'll start to see is you'll start to run into regions where, you could actually do an ellipse problem with polar. It's going to be a little bit more complicated than you would want it to be. So we're going to do a set of custom coordinates for this ellipse-shaped region. Anytime you see a parallelogram, anytime you see an ellipse, those are regions that are a really good candidate for custom coordinates. To make your custom coordinates, all you need to be able to do is parameterize your region. If you could parameterize a region, you can integrate over a region. So this is not quite polar coordinates, right? Because we have this extra 2 in here. So this is a parameterization of our ellipse that goes 2 units in the x direction and only 1 unit in the y direction. Our u goes from 0 to 1. That's to fill in the space inside of that ellipse. So we're parameterizing a filled-in ellipse. And then, of course, since it's a full ellipse, our v, our angle, is going to go from 0 to 2 pi. Because we're not using polar, we do have to do an area conversion factor calculation. It's really not too bad, though. dx du, well, that's fairly easy to calculate for 2u cosine v. Dy du, well, that's not very difficult to compute with u sine of v being your y, so on and so forth. So you get 2 cosine v, sine v, negative 2u sine v, u cosine v. Take the determinant of that 2 by 2 matrix, simplify using the Pythagorean identity, and you get 2u. Not too surprising, it's very similar to the polar coordinates area conversion factor, but this extra 2 is accounting for this little change in the x direction. If your ellipse has a change in the x direction and the y direction, you'll probably notice that that Jacobian determinant, that area conversion factor, will probably be the product of those two shifts. One trick that you might notice is this area conversion factor. The two columns in that 2 by 2 matrix are actually gradient vectors. We have dx du and dx dv, which is the gradient of x of uv. Likewise, the second column, you might notice that that looks a lot like the gradient of y of uv, dy du and dy dv. So you could always think of an area conversion factor as columns of gradient vectors. That's one way to remember the formula if you ever get stuck. Good way to remember this formula. I think you'll see it pop up in the lit sheet, but you can think of the area conversion factor as a determinant of a pair of gradient vectors. One that comes from x of uv, the other one that comes from y of uv. Alright, so now we can crunch the numbers on this calculation. Notice that it is not an area calculation. This is a volume calculation. You can imagine the surface z equals y squared floating above this ellipse, but we don't actually need a perfect picture of it to be able to do this computation. You don't need to be able to picture that surface necessarily. Alright, so I'm going to replace all instances of y with my y of uv equals u sine v. And then I have to put my area conversion factor into the problem. Now what's cool about this is we have mapped to a UV coordinate space where this ellipse is actually a rectangle. So in this UV space, U goes from 0 to 1, and V goes from 0 to 2 pi. And let's compute our integral over our UV space rectangle. All right, so I'm going to take the factor of 2 out. I'm going to squish the u squared and the u together into a u cubed. I'm just going to do this a piece at a time. So the u portion of the integral we can do first. Plug in u equals 1 and u equals 0. Then we have, take this 1/4 out. So now my factor is a 1/2. 1/2 times the integral from 0 to 2 pi of sine squared of v dv. And I could have given you guys this single integral last year, so you could finish that on your own. You get pi over 2. Integrating over a UV space rectangle is a lot easier than integrating over an XY space ellipse. But we're done. All right, here's a change of variables that's going to be aided by Mathematica. I'm integrating over a parallelogram-shaped region. This one has to be done using Mathematica, not because of the parallelogram, but because of this integrand of e to the y. It's going to make things a little bit complicated. On your triad problems, this would be similar to a triad problem. If I were to tweak this integrand, it could be a lit sheet problem, it could be a quiz problem. All right, the first trick is to look at the sides of your parallelogram and just find the equations of those lines. So, not too bad right there. We have a pairs of sides of parallel lines for our parallelogram. You could rewrite those. So if you have, say, y equals x plus 1, you could rewrite that as 1 equals y minus x. If you have y equals x minus 4, you can rewrite that as negative 4 equals y minus x. You already might see where this is going. Because you kind of have a u, you kind of have a v, and you kind of have numbers that those are varying from. U goes from between negative 4 and 1, or v goes between 13/4 and 6. So I'm going to do that. I'm going to say let u equal y minus x, let v equal 1/4 x plus y, and let u vary between negative 4 and 1. It's kind of like filling in the parallelogram in that direction, right? And then v goes from 13/4 to 6. It's kind of allowing the parallelogram to go out that way. We kind of have our substitution, but we also kind of don't, because when we're finding our area conversion factor, we need our map that goes from UV space into XY space rather than the other way around. So you don't usually want to write U as a function of X and Y and V as a function of X and Y. I need X as a function of U and V and Y as a function of U and V. Of course, it's just a little bit of algebra to switch between them, though. For example, if I were taking a quiz, I would say, okay, U equals Y minus X, and V equals 1/4 X plus Y. Oh, you know what? If I multiply this equation by 4, so kind of doing a little substitution here, this becomes 4V equals, let's see, that's going to become X plus 4Y. But my other equation, I'm just going to reorder the terms on the right side, but it's U equals negative X plus Y. Oh, wait a minute. So I have U plus 4V equals, the X's cancel, and I have 5Y. And that becomes Y of UV equals U plus 4V over 5. So I solved this system of equations, and I found Y as a function of U and V, which is what I needed. You would do the same process using just your good old Algebra 1 knowledge to find X of U comma V. And then you have your map that goes from UV space into XY space. X as a function of U and V, Y as a function of U and V. Of course, this is a Mathematica assisted problem because that integrand is so ugly. And Mathematica is very, very good at solving systems of equations. So on a triad problem, you would just let Mathematica do the work. On a lit sheet problem, on a quiz problem, you would do what I just described. Here's the command that you would plug into Mathematica to have it solve that system for you, because you don't want to do it by hand if you don't have to. And you could see my Y of UV is the same as what I just found by hand. X of UV, if you were to do that by hand, there's what you would get. All right. So make sure that you understand that Mathematica is solving a system of equations when it runs this solve command. The only thing I worry about is we're going to do a bunch of triad problems and not much by hand practice till the end of the chapter. Every time you press Shift-Enter on one of these solve commands, you should be thinking about how, hey, this is a system of equations that I could solve by hand if I needed to. You don't want to walk into the quiz not knowing how to finish the problem because you forgot that you're solving an Algebra 1 system of equations. Anyway, now that we have our X of UV and our Y of UV, we need to find our area conversion factor. Really, it's just a couple partial derivatives, nothing too crazy here. For example, dx du, you would take this x and take the partial derivative with respect to u. Remember, you're treating v as a constant, so this derivative would end up equaling negative 4/5. You could do that for all 4 entries in that matrix. I'm not going to walk through every one of them, but you guys can double check those partial derivatives, make sure you agree with them. Then we're going to take our 2 by 2 determinant. We're going to get negative 4/5. Now, there's nothing wrong with a Jacobian determinant coming out to a negative. There is a meaning to that negative, actually. It's saying that between your UV space and your XY space, you're reversing the orientation of the curve. But when we crunch our numbers, we're going to use the absolute value of the area conversion factor, the absolute value of the Jacobian determinant. So we're going to be using 4/5. In general, when you're double integrating, if you get a negative number, or if you get an expression that can become negative for part of your bounds, you want to use the absolute value of that area conversion factor. One way to think about it is area is only ever positive, and so that adjustment factor shouldn't be allowed to go negative in your double integral. But the negative's not wrong, it's just it's not something that we want to use when we're accumulating. Remember again, you do want to notice that the columns of these area conversion factor matrices, the columns of these Jacobian matrices, are actually gradient vectors. So keep that in mind. If x of uv is this expression that we found, then the gradient of x makes up our first column of our Jacobian matrix. Same thing for the y column. It's the gradient of y of uv. Anyway, let's crunch some numbers. So we have everything we need. The absolute value of the area conversion factor is 4/5. We know x of uv and y of uv. Y of uv is going to be useful because we're going to plug that in for the y and e to the y for our integrand. And we know our limits of integration. So what looked like a parallelogram in this new coordinate space is a rectangle. So we're integrating over a rectangular region. It's ugly. This is difficult to integrate without Mathematica, or at least it's more pleasant to integrate with Mathematica. And you get 417.1 when you run it through the computer. And just a reminder here, the big secret to all of this, the big observation that you should come away with. I know there's a lot of technical details with finding the area conversion factor and all of the work that goes into crunching the integrals, but from a big picture perspective, every one of these problems starts with a parameterization. I don't care what your XY region looks like, no matter how weird that XY region looks like. If you know how to parameterize it, you know how to integrate over it, because a parameterization is a change of coordinates. If you could parameterize a region, you could probably integrate over it, because most likely your parameterization is a mapping from your weird-looking XY region into a UV region where you actually have a rectangle. And then that's nice because the bounds for your parameterization are your limits of integration for your integral. Alright guys, thanks for watching, and I hope this was a helpful video. In terms of deadlines, remember that we are sticking with our original try-it deadlines, so you do want to start try-it 1 and 2 at home. And if we do have continued severe weather days, say Wednesday or maybe Wednesday and Thursday, who knows, we'll just be checking try-it problems online. Alright, have a great day. Bye-bye.